Okay, so welcome everyone. My name is Juliet Bruce. I'm a postdoc at UC Berkeley and also on the board of Spectra, the Association for LGBTQ plus mathematicians. And thank you so much for joining us today for the first inaugural Spectra Lavender lecture. So the Spectra Lavender lecture is a new thing we're trying to do to honor LGBTQ plus mathematicians who have made significant contributions to the mathematical sciences, mathematical education, and the mathematical community at large. We're honored today that the first Lavender lecture will be given by Professor Autumn Kent at the University of Wisconsin, Madison. Professor Kent embodies all of these traits through both her exceptional and innovative research in geometry and topology, as well as her thoughtful support and mentorship of students and LGBTQ plus mathematicians. And we're honored to have Professor Kent today talk to us about families. I will turn the floor over to Autumn. Thank you all for joining us.
Thank you, Juliet. It is quite an honor to be invited to give this inaugural Lavender lecture. Especially, since for a lot of my life, I didn't really feel like I was part of the queer community and sort of felt a little outside of it. I don't even like Kate Bush, so why, you should just cancel my invitation to give this lecture. But, as you grow up, you as time goes by, you find your people. And so the community doesn't have to be homogeneous, for you to be part of it. It makes family interesting if there's a little dysfunction and there's a little variation in everybody, and there's all kinds of people. And I don't want to talk too much about life, but one thing that's kind of wonderful about mathematics, it's kind of unique, I think, it's uniquely accepting of eccentric people, so the math community, a lot of times, you can be pretty eccentric and people will just accept you just fine as a mathematician. You can hang out and people from all walks of life, end up becoming, close friends and collaborators. And so that kind of gives me hope, even though mathematics as a culture isn't perfect by a long shot. I think this tolerance that's built in sort of gives me hope that we can continue to make the community that we do have better as time goes on. So I think a lot about families. So here's a picture of a ragtag group of stick figures. I think about families mathematically quite a bit, and they also come in all different kinds. So that's what I want to talk about today. So I want to start out by talking about asteroids, which is this is my favorite thing to talk about, probably. So I don't, I'm not an astronomer or anything. So I mean, if you're old enough, you might have had an Atari when you were a kid, like I did, and you played a video game, on your television. And so when I was a kid, my television didn't look like this. It looked like a 4:3 television, which is more like a square. And so this is my TV now, which is a 16:9 TV. And you can't tell how big or small my TV is by this drawing, and so you have a 16:9 TV, and whether or not you have a 7,000 inch TV or not, depends on how much you like football or whatever you like to watch. So here's a TV. This is my TV, and I'm going to play this game of Asteroids on it. And so if you're not old enough, this is a video game where we have a little ship captain, and she flies this little kite-looking spaceship. And when she flies into the top of the television, she comes out on the bottom. So you can see that here. And then, she hits the top again and comes out in the lower right-hand corner, and then hits the side and comes out on the left side. So, and then there's a bunch of little asteroids, floating around. Those little, they look like animated crumpled paper, pieces of paper. And you shoot those and they break up into smaller asteroids, and then eventually they disappear. So you fly around, and there's no friction or anything, and you live. And this is, as a mathematician, this is happening on some torus, And so this little ship captain, she lives in this little torus, and she spends her life there's nothing else in the universe except her and these asteroids and her lasers. And so she just spends her life in the ship shooting asteroids, and the lasers go off the edge of the screen, and she's just on this torus. Now we could have a different shaped TV. You know, maybe this is like you want to watch Stanley Kubrick movies or something. You have a TV like this, and you know, we could pick the ship captain and her ship, and those 3 asteroids that I've drawn, and we could just pick them up and draw a little lasso around them and pick them up and take them over into this other TV, preserving distances. And just now she lives in this TV. And you know, if you just did that, so suddenly she would notice that she's on a collision course with the asteroid that maybe she wasn't on a collision course with before. So if she goes on this, she has, you know, on the left in the regular TV, she can go on this long kind of trip and not hit anything. But in this second sort of skinny TV, you know, after a short amount of time, maybe half the time or something, she's going to hit this asteroid if it doesn't get out of the way. So this TV really feels different to her right away. You know, if she flew around it long enough, she could actually, you know, figure out that she's been transported to a different universe, a different television. And she could do that by, say, finding this path. So she might end up later on in the day on that trajectory, and she'd go around the TV on this little loop. And that loop has some length, so she could have this path of a certain length. She could, you know, throw out a tow line and hook it to her own ship and tow herself forever. But that tow line would have some length that didn't ever occur in her other universe. So she could actually tell if she was industrious enough and clever enough to figure this out. So she noticed her world was different, and she could figure it out by being in the television. Also, you know, feel free to shout out and ask questions or complain. So now, if we could do this again, we could put her in another universe. Let's transport her again in her sort of like TV multiverse of TVs, and I could put her in a TV like this. Okay, and I've done the same thing, and I've picked up her and those asteroids kind of isometrically. But you notice that the big asteroid kind of wraps around the TV. The TV is very skinny. If I put her, I run into trouble, like if I made it a little skinnier than this, like twice as skinny, then it might just crush the ship. Like her ship wouldn't even sit inside, it'd be too big. Okay, so that's these are a bunch of TVs that you could have, and these are a bunch of ways you could play asteroids. And we can always ask this question, like, would the captain be able to tell that we moved her? And so in all 3 of these cases, she could figure it out, because like each TV has a curve that's shorter than any curve in the previous ones. Okay, so we could also put her in a parallelogram TV. Okay, this is annoying to watch football on. And we could do the same thing. I picked her up and I put her in this other television. And you know, and to us, it's clear that, like, you know, things have kind of moved around. It's a different television to us. But now we kind of wonder, like, would she be able to tell? Okay, and well, this parallelogram, well, I could kind of cut it in half along that vertical line, and I could move you know, that triangle on the right back over here, and you know, I'd see it's the same. The universe of the TV is the same as a square, a rectangular TV. And so actually it's the same picture from her perspective. It seems like nothing happened. She wouldn't notice at all. Okay. So let's turn the TV off. Okay. Well, wait a minute, I want to go back to this. Okay. So let's look at this again. So what did we do before? We picked her up in the asteroids and we put her into this torus isometrically. We didn't change any distances, you know, at least on small scales. Well, this is this is a parallelogram, and there's some linear map. There's some affine map that I can take this rectangle and I can send it to this parallelogram. Okay, so I can just shear I don't know which way, if I'm reversed in your image or not, and I can put her in using that affine map. Okay, And now she would notice, okay, so something has happened about her immediate experience. You know, in particular, the length of this trajectory has changed. And she's kind of gotten squished a little. You know, I don't know if she would notice that. I don't know anything about relativity. But again, you know, this is the same TV, you know, universe as we had before. And so, you know, in the original TV, if we had the regular TV, like we may as well think of it as the regular TV because they're the same universe as far as Asteroids is concerned. Like she would look like this, you know, if we were watching someone play Asteroids in this new, you know, in this new version. So it's like it's the same universe, but the TV is, so it's the same TV, but it's wearing Asteroids in a different way. So it's like Asteroids is like a shirt, you know, this is like a t-shirt that the TV is wearing, and we just put it on in some funny way. We put it on with our head through the arm or something. Okay. So there's all these universes of TVs, and some of the TVs give you the same universe. But if we kept track of how the TV was wearing Asteroids, then we'd have lots of different things. So we're going to start to kind of distinguish between those two situations. Okay, so let's forget about, let's be more serious for a second. And let me just call this parallelogram, which is just a rectangle, P, and then I have some other parallelogram, Q, and again, I have some affine map between them, okay, that takes the bottom to the bottom and the left side to the left side. Okay, so this is like a map between TVs. Okay, and then I want to measure like how different are these TVs, like, you know, from the, you know, ship captain's perspective being put in TVs by affine maps. And so if I take a little circle on this rectangle and I hit it with this affine map, it goes to an ellipse. Okay, and if I look, I'm getting older, I need glasses, and you look at this ellipse a little closer, then it's sort of longer in one direction and shorter in another direction. So, you know, if it were a circle, you know, there's no preferred kind of directions, but here there's a sort of long axis, a major axis of length m, and then there's this minor axis of length little m. Okay, and if I take their ratio, that kind of measures how extreme this affine map was. So if it were actually a circle, I maybe just rotated my rectangle or reflected it or something. So I have this ratio that kind of measures how far apart these two parallelograms are. And if I literally wanted like a distance function on the space of TVs, I could take the log of it. Okay, and so I'll define the distance between these two parallelograms to be log of m over m. Okay. Okay, so that's sort of a very nice elementary way to think about this stuff. Okay, so, but let me start again. So I'm going to just keep starting over. Okay, so here is my parallelogram, and just to make sure that I'm not being oversimplistic, let's actually make it look like a proper parallelogram. Like, I don't know if my kids are in school, I don't know if their teachers consider a rectangle a parallelogram or not. So here's the parallelogram, and what I'm going to do is I'm going to put it in the complex plane. Okay, and I'm going to put this lower left corner at the origin. And you know, before I was talking about I have a 16:9 TV, and I don't really know how many inches the TV is. So we really only care about TVs up to scale because we just care about the shape of them. And that's the quality of the viewing experience for the most part. And so instead of worrying about, you know, I could, the easiest, there's two ways I could do this. I could say, well, I'll scale so the TV has an area 1. Okay, that's kind of a natural thing to do. And so what I'm going to do here is I'm going to do a kind of unnatural thing, and I'm just going to scale it so that the bottom has length 1. Okay, just for simplicity. Okay, and then if this is sitting in the complex plane, this upper left corner is some complex number omega. Okay, and then if I have some other parallelogram, it has some complex number tau. Okay, and it's just completely determined by this one number. Okay, this complex number. So instead of P and Q, I'm gonna name the parallelograms by these complex numbers. And so then it's like a funny kind of statement. You have an affine map between omega and tau. So omega and tau are complex numbers, but I'm identifying them with these parallelograms. And so, you know, there's some major to minor access ratio I could think about. But then a slightly fancier way to do this is to use complex analysis. And so what you do is consider this thing called the Beltrami coefficient. And so it's the z bar derivative over the z derivative, if you remember complex analysis. And the point is that if the map is conformal, then this is 0. And so this is kind of like basically this major to minor access ratio kind of thing. And if you take its size, that'll be less, you know, less than 1. Okay. And so then you take that number, which is less than 1, and then you do the obvious thing and take the log of this ratio, and then that's a distance function on the set of, on the upper half plane in the complex plane, considered as, you know, the space of parallelograms. Okay. Now this is called the Teichmüller distance, and I can go, now that I have these parallelograms, I can go back and I could say I can identify, I could re-identify the sides of my parallelograms, and I'd get a space of tori. Okay, so I have a space of universes for my ship captain, and that's called the Teichmüller space of flat tori. Okay, and now you know, it's obligatory at this point to talk about Teichmüller for a second. And so Teichmüller was, especially given the nature of this lecture. So Teichmüller was an early 20th century mathematician, and he was a dedicated member of the Nazi Party. So there, you know, he worked against Courant and Landau. He basically converted Bieberbach to the Nazi Party and to Nazi ideals. And so when you hear things like the Bieberbach conjecture, and you hear about Bieberbach all the time, you take, you know, introductory mathematics. And it's important to remember that, you know, we're not all great people, and like, we're not all, you know, some of us are doing bad things, and some of us, you know, are, you know, we're all capable of doing things that are harmful to others. And it, you know, there is a movement to change the name of this space, you know, to get rid of his name. But I kind of am against that. I think it's worth having this remembrance all the time, and to, you know, and so when Beers, you know, Beers was a, you know, Jewish mathematician, and he thought Teichmüller's work was beautiful, and he quoted Plutarch, and so he said, you know, just because I think someone's work is beautiful doesn't mean they're not a jerk, you know, where jerk is a very mild word, you know. Recently, I also learned that Kähler, you know, you hear the words Kähler-Einstein all the time, which is like Kähler's name next to a Jewish name. And Kähler was a Nazi who survived the war. Teichmüller died in battle. And Kähler survived the war, and like, he never stopped being a Nazi, and like, you know, until the end of his life, until the second half of the 20th century, you know. And, you know, I guess, you know, they say he had a Nazi flag in his office, you know, so this is like, yeah, so I think knowing these things like helps us keep an eye on ourselves. Okay. Anyway, so who cares about that guy? Okay, so okay, so this is the Teichmüller space of flat tori. So the space is beautiful. Okay. And now I want to start over again. Okay, so I have this Beltrami coefficient, and I can define the distance in that way. And so what are, you know, it turns out that this is not just a metric space. So it's actually a metric space, and there's geodesics in it. So it's a geodesic metric space. And so the way to think about that is so now I'm thinking about everything as a torus and not just a parallelogram. And so what I'll do is I'll take a holomorphic one form phi dz on the torus. Now on a torus, these aren't super interesting. Like it's like basically a constant times dz, but there's a complex number worth of yeah, so we have this distance. There's a question in the chat, sorry. The space is a metric on C. So it's only a metric on the upper half space. So everything where the imaginary part is positive. So you take this holomorphic one form on the torus, and then by the fundamental theorem of calculus, if you integrate it, you get a coordinate. Okay, now this may seem kind of silly in this setting, but later on we'll come back to this. So we get a coordinate and to the complex plane. So on the torus, we have some torus living abstractly, and we have some naturally defined coordinate system on it that's mapping into the complex plane, somewhere else. And if we pull back, the imaginary, the vertical lines in the complex plane and the horizontal lines, okay, you have these two foliations of the complex plane corresponding to horizontal and vertical lines. And if I pull those back by this natural coordinate, I get a kind of a horizontal and vertical lines, real and imaginary directions on my torus. Okay, and so I have these two perpendicular directions. And now if I take, there's a natural way to kind of stretch the surface in one direction and contract it in the other. And that gives me a geodesic path as I vary T. Okay, so think about if your affine map were actually diagonalizable, and then you have these two eigenspaces, and this is exactly what's happening. It's like the eigenspaces of your affine map. Okay, so these are geodesics. Okay, and y'all should look at Dave Fooder's comment in the chat. Okay, so what does that geodesic look like? Well, amazingly, it looks like this. So here's our two parallelograms, omega and tau, and the geodesic between them is a circle, and the circle is like orthogonal to the real line. Okay, and if you've ever installed Venetian blinds, you're familiar with this because it's most efficient to move Venetian blinds when the bottom is on the floor, to move the top of it in a circle than it is to just shank the top of it to the left or the right. It's like there's less resistance. So that's actually, physical representation of this. Like it's easier to move Venetian blinds in an arc than, okay. Okay, so there's our geodesic in our Teichmüller space of flat tori. Now I know another metric on the upper half plane that has this property that geodesics are circles or half circles. And that's called the Plonkery metric. Okay, Plonkery is a much neater person than Teichmüller. Apparently, he would go on long walks, and one time he was clenching his hand because he's thinking, and then he got to the end of his walk and he realized he was holding a basket that he didn't have at the beginning of his walk. Okay, so here's the Plonkery metric. He's a smart fellow. He also independently discovered special relativity, so he's no slouch. So the line element just looks like this. So you just scale, you divide by y as you move around in the upper half plane. And so this is called H2. And so by an incredible, I don't know if you call it a coincidence, the Teichmüller metric and the Plonkery metric are exactly the same, up to like a factor of 2 or 4 or something. With my normalization, I think it's 2. Okay. So that's kind of amazing. So this is well-studied space. This is the hyperbolic plane, and nice model of Lobachevskian geometry, and the group of isometries is basically SL2R, not quite, but and so it just acts on the upper half plane by linear fractional transformations, and if you think of it as the Teichmüller space, then the SL2Z orbits are exactly the isometry classes of tori. Okay, and so if you take the quotient of H2 by this, you get the moduli space of curves, or the moduli space of flat tori. And in the example at the beginning, it's just the matrix 1101 that takes our TV to the other TV. Okay, how are we doing? So here's the Plonkery metric. Okay, equal to this Teichmüller metric. Okay, now this is perfect timing because I want to transition to thinking about more complicated spaces than tori. And so if you have a surface of genus G that's bigger than 1, then they have hyperbolic metrics. So they, instead of being flat, they look like H2 locally instead of looking like the plane locally. And so here's an example. This is actually a genus 2 surface with a point removed. So here's an octagon. This is a gray octagon in the hyperbolic plane. And it's missing its vertices. So it's like, these are all geodesic lines in the hyperbolic plane. And that's an octagon because there's 6 little humps at the bottom and then 2 top and bottom. And I just kind of identify opposite sides on the octagon, and then that'll give me a hyperbolic metric on a surface, okay, of genus 2 with 1 puncture. Okay. Now, when I started out with flat surfaces, this flat tori, I could deform them. There's lots of parallelograms, and like some of them are close together. I have this distance function, and it's this nice continuous space. Well, I can deform the conformal structure. Now you kind of think about the conformal structure. I could deform the hyperbolic structure on a genus G surface, and maybe that's not as obvious. There's no similarities anymore. There's no obvious operations to do. But like, here's this octagon, and all I said was identify opposite sides. So go ahead and do that in the obvious way. And then there's another, it's like an inchworm or the slinky or something. And, I could do that in a bunch of different ways, and I'll get different genus G surfaces, okay? And they're conformally different. Like this loop in the middle, it's kind of like that example at the beginning of the talk. The loop in the middle of this really long inchworm, it turns out in the hyperbolic metric that, it'll have to be pretty small. So you think of the hyperbolic plane, the metric gets tiny as you move up. So you're dividing by y. So as this arc gets higher and higher in the hyperbolic plane, that vertical loop is going to get small. Okay, but it's hard to think about an octagon that way. So let's just think about a stop sign. Okay, and I want to think about deforming the hyperbolic metric, and it's actually easier to think about deforming the conformal structure, which if you go back and think about the flat surfaces, that's the same thing. Okay, we're just measuring the Beltrami differential measures the deviation from being conformal. So what I'll do here is, instead of a one form, I'll take what's called a holomorphic quadratic differential. Okay, so it's like a holomorphic function phi, times this dz squared. Okay, whatever, it's some differential. Okay, it's a section of some bundle. Okay, and so again, you have a natural coordinate. You take the square root of phi and integrate it, and you have the same thing. And then it's a coordinate away from the zeros, and at the zeros, it's a branched coordinate or something. Okay, but the same thing happens where you can pull back the horizontal, the real and imaginary directions everywhere. You pull back the complex structure basically, and you see these horizontal and vertical directions again on the surface. And again, there's geodesics in this. You have a metric again called the Teichmuller metric, and the geodesics look like this. And the metric is defined almost literally the same way. And then if it turns out that this space, just like the upper half plane is homeomorphic to R2, this is actually homeomorphic. In the closed case, it's homeomorphic to a ball, so it's R6G minus 6. Okay. Okay, so that is kind of families of Riemann surfaces. So that's what we were talking about. So if we have hyperbolic structures, we can deform them, and like you can deform them through hyperbolic structures that are complete hyperbolic structures. So they're Riemannian metrics, and they look locally like the hyperbolic plane, and the metric spaces are complete, and we can do these deformations. Okay, so that's the kind of thing I study. And but most of the time I'm thinking at one dimension up. Okay, so I want to talk about something that maybe outsiders don't see a lot. And so I want to talk about families like this in higher dimensions. Okay, so let's talk about hyperbolic 3 manifolds. So we had hyperbolic surfaces, that's things that look like that metric space H2 that I talked about earlier. And so what's H3? Well, it's the upper half space. So you take the complex plane cross R, and then look at the part where the real number is positive. And so here I've drawn the complex plane as the floor of hyperbolic space. It's like at infinity. And then hyperbolic space is everything above the complex plane. And you have a Plonkery metric here, and it's the same thing you did before, except now Z plays the role of height. And there's copies of the hyperbolic plane in here all over the place. So there's any vertical plane, half plane will, metric will just restrict to something that looks like that metric we had before. And then also amazingly, hemispheres that are orthogonal to the complex plane will actually be copies of the hyperbolic plane. Okay. And then if you look at this thing, like the isometry group isn't SL2R anymore, it's basically SL2C. Okay. And the action is like linear fractional transformations on the complex plane, and then those extend somehow to isometries. Okay, so we're not going to worry about it. Okay, okay. So before I continue, I need to explain one other aspect of this hyperbolic space that I didn't talk about in the plane, and that's what's called a horosphere. Okay, I don't know the history of this name or the etymology of this word. But a horosphere is just, the basic example of it here is just a horizontal plane in hyperbolic space that's not C, it's actually in hyperbolic space. So it's a positive height horizontal plane in the upper half space. And it's just you know, a point cross C, okay? And you know, that's not, so that has a nice flat metric that it inherits from the complex plane. That metric is not, you know, doesn't behave super great with respect to the hyperbolic metric, but anyway, there's a natural, you know, sort of flat structure on this plane. So that's what I need to know. Okay. So I want to talk about hyperbolic 3 manifolds. So here's an example of a hyperbolic manifold. So I said earlier that a hyperbolic surface is you take, you know, a surface and then you have a structure on it where it locally looks like the hyperbolic plane. And that's what a hyperbolic 3 manifold is, except, you know, it locally looks like hyperbolic 3 space. And so the thing to say is that there's some discrete subgroup of PSL2C, and it acts on hyperbolic space, and the quotient is the manifold. So that's a hyperbolic manifold. And now here's an example, a famous example called the figure 8 knot complement. So if you take, this is the figure 8 knot, and if I delete it from the 3 sphere, I get some non-compact 3 manifold. And then it turns out that there's a hyperbolic metric on that. So you can build that thing as H3 modulo some discrete group of isometries. Okay. And you can actually build the hyperbolic metric explicitly by hand, which is kind of beautiful. Well, it's not kind of beautiful, but anyway. So this is a hyperbolic manifold, okay? And now you might say, what does it look like near the knot we drilled out? Well, when I have a circle in the 3 sphere, I could take a little regular neighborhood of it, and it's like a solid circle, just like a disk across a circle. And so if I delete the core of the solid torus, then it just looks like, you know, kind of like a torus cross array topologically. So there's actually this cusp here. And so the distance as you go out to the cusp gets smaller and smaller. So it's a torus cross array. And then as you go out to that sharp point, the diameter of that torus goes to 0 exponentially fast. That's kind of a rough picture of the geometry. Okay, and so at this cross, you know, I'm talking about I have this torus here, but I claim that there's a nice torus in there, and I'll call it a horospherical torus. And so what does that mean? Well, that means that actually there's one of those horospheres in hyperbolic space that actually is covering that torus downstairs, and the torus downstairs is embedded. So let me go back for a second. So here's a horosphere P, and the claim is that basically when you hit P with this group, or the stabilizer of that plane or whatever, that you'll get that torus downstairs, and that torus is embedded. So you'll notice here in this picture, I've drawn the fundamental domain for the group, the stabilizer of this plane acting on it. And so I get a torus in the quotient. So in this flat plane, I have a parallelogram that is mapping down onto my torus, and I'm just identifying opposite sides, just like at the beginning of the talk. Okay, so not only there's a horospherical torus here, it's a cross section of this cusp, and it has a natural flat metric that's defined up to scale. Okay, so it's actually, so this is like flashback to the beginning. So somehow our original picture is showing up here in this 3-dimensional picture. Okay, now this particular manifold is finite volume. So it's a Riemannian manifold. It has some volume form, and you could integrate it, and you get some number. And well, there's a theorem, you might ask, like, just like in the lower dimension case, in the dimension 2 case, where we could deform hyperbolic metrics, like you could take a hyperbolic genus 2 surface, and we could stretch the slinky out and get a new hyperbolic metric. And we can do that, like there's a continuous family of those genus 2 surfaces. Okay, so we go up a dimension, and now we're asking that this finite volume hyperbolic manifold, just like that finite volume genus 2 surface with one puncture, you know, now instead of deleting a puncture, we're deleting a knot. And, you know, you could ask, like, can I deform this hyperbolic metric? Okay. And I want some restrictions on that deformation. Like, I don't want to, you know, deform it to some trash metric. You know, I want it to be a hyperbolic metric still, and I still want it to be complete. Okay, I want to have, you know, complete metric spaces are kind of the nice ones. So Andre Bay showed that there aren't any. Okay, so you can't deform, at least locally, like you can't, there's no continuous deformation of this hyperbolic metric through complete metrics. So that's kind of stinky if you care about families like this, you know. And then Mostow and Prasad showed that the hyperbolic metric is unique. So not only are there no local deformations, there's basically no other hyperbolic metric at all. Okay. Well, that kind of, you know, puts the kibosh on the talk, right? So, so you kind of get this impression that maybe, like, if you look at the set of all hyperbolic 3 manifolds of finite volume, it's just a bunch of lonely 3 manifolds just floating all by themselves, you know, with no friends, right? And so there's like, they stand apart. But there's this theorem of Jorgensen that says that the set of volumes is omega to the omega, which just sounds cool, right? Well, omega to the omega is an ordinal number, and you can think of it sitting inside of R, and it's like a sequence of points, and then they start to accumulate somewhere, and then you have another accumulation point, and then the accumulation points start to accumulate, and then eventually they accumulate on a kind of a second order accumulation point. It's an accumulation point of accumulation points, and then there's a third one where it's the first accumulation point of accumulation point of accumulation points, okay, and so on. And so that's omega to the omega. And so this is the set of all the volumes of hyperbolic, complete hyperbolic 3 manifolds. And now, but if you look at that, it seems like they're not alone, right? You know, so here's the, you know, the one at the very left is the smallest volume closed thing, which is kind of like, why is it closed? And then the first accumulation point is the smallest one cusped hyperbolic thing. So where you've kind of like drilled out you have one knot missing. And then the first accumulation point of accumulation points is the smallest 2 cusped thing. Okay. And then the next piece in the ordinal number is like the smallest 3 cusped and so on. And so it doesn't seem like they're alone. Okay. Now, you know, by kind of Bayes' theorem, we kind of expect that these nearby ones aren't the manifold that the accumulation point corresponds to. And it turns out that the accumulation points coming from a topological, they're there for a topological reason. Okay, called Dane Filling. Okay, so here's our cusped manifold. Okay, and infinite things, you know, they can be annoying, right? Learned in the end of the 19th century. So I like compact things, so I'm just going to cut the cusp off completely. Okay, and I get something that's kind of like M, so I put M in scare quotes. Okay, so the interior of this compact manifold is homeomorphic to our original thing, but we don't really care so much about that. So now I have this thing, and it has boundary now. It has a torus for boundary component. And I could take but what I could do is I could take a solid torus, okay, and I could glue it to that torus boundary. I could glue the boundaries together. Okay, and now there's lots of different ways to do that. Okay, like if you think about the figure 8 knot, we drill out a little neighborhood at the figure 8 knot. We could put the solid torus back in and get the 3 sphere. But we could put the torus in sideways if we wanted. So if you take any simple closed curve, essential simple closed curve on this boundary torus, then if you look at this disk across the circle, there's basically a unique loop on the boundary of that torus that bounds a disk. Right? It's basically boundary of the disk across a point. That loop It's kind of special in that it bounds a disk in the solid torus. And there's basically a unique way to glue this donut, the solid torus, to the 3 manifold so that the boundary of that loop mu, that special one that bounds a disk, is attached to alpha. So, you know, topologically, you kind of think of, you're just adding a disk to alpha, okay, and then capping off of the ball. Okay. So that's called Dane filling. So that's called the alpha Dane filling of the manifold. And when you do that, like if we had one cusp to start, when we do that, we get a closed manifold called M alpha. Okay. And I just draw that. It's kind of like rounded off. There's something there now. Okay. Okay, and so we could do that. There's infinitely many alphas we could choose. And Thurston proved a beautiful theorem called the hyperbolic Dane filling theorem. And it says that all but finitely many of them are hyperbolic. So what does that mean? It means that they too are quotients of hyperbolic space by some discrete group of isometries. Okay, so that's a beautiful theorem. And how does he do this? And so what does he do? Well, he deforms the manifold through hyperbolic metrics, okay? And you might say, well, that's contrary to what you said a minute ago. But he deforms them through incomplete hyperbolic metrics. So this is kind of funny. So you take this original cusp manifold, and then what he shows is you can deform the metric through metrics that aren't complete. But you can make a really tiny deformation and get an incomplete metric. And then when you take the metric completion, all you do is add a geodesic back in, and then you get a hyperbolic manifold. Okay. So not only can you deform a little bit, get an incomplete metric, take the metric completion, get a hyperbolic manifold, when you do that small deformation, you're not changing the volume very much. Okay. And so it turns out that as you do, you know, you're doing these deformations, you know, the volume doesn't change very much. And so actually, let me come back to this parenthetical. So what's happening is like you have this one cusp, smallest one cusp thing. Then nearby, there's a bunch of incomplete metrics whose metric completions have roughly the same volume. And that's where these accumulation points are coming from. And like, one way to think about the deformations that he does is that you're deforming the flat torus cross section, and you're not actually deforming through, you know, through flat structures. Strictly speaking, you're kind of deforming the affine structure, but that's for the experts, so they don't yell at me. Okay. Okay. So so that's cool. Like we used a different kind of family. You know, we enlarged our idea of what family was in order to prove the theorem, or Thurston did. Okay, so another way you could do that is like, we can think of this hyperbolic structure as a discrete and faithful representation of the fundamental group of the manifold into the isometry groups of hyperbolic space. So that's the group acting on hyperbolic space is isomorphic to your fundamental group. And I could think about a different way of varying the hyperbolic metric. Instead of varying the hyperbolic metric, I could just vary this representation. So there's actually a whole large, you know, there's a whole menagerie of homomorphisms from the fundamental group into PSL2C, and I could just consider all of them. Okay. Now, like the trivial representation is in here, so that's, you know, some of them don't correspond to anything interesting. But if I sort of mod out by conjugation, which it doesn't really do anything interesting, then I get this thing called X, and it's called the character variety of X. And you know, so this is like some you know, some family of representations into the isometry group of hyperbolic space, and so it's a different kind of family. And so inside of here is kind of like all of these incomplete hyperbolic metrics that Thurston constructed, but then it contains all this other stuff. But the reason I'm mentioning this is like, it's a different type of family, but what he's actually showing is that like this variety, so this is actually a variety, and you have an algebraic curve that passes through this representation corresponding to this hyperbolic metric. And the algebraic curve is actually, you know, for one cusp thing, it's well defined. And it's actually an invariant of the manifold. So if you have a hyperbolic 3 manifold with one cusp, then associated to it is some algebraic curve. Okay, and so like you can start asking questions like, what's the genus and what's the algebraic geometry of this curve? And so you have a hyperbolic 3 manifold, and suddenly you have some interesting algebraic geometric object. Okay, so just thought I'd mention that. So this is a totally different family. Okay. Okay. So now that's like the finite volume picture. While we're here at Thurston's theorem, I should say that if you're brave and you go into higher dimensions, then if you take a finite volume hyperbolic 4 manifold, then Wang showed that there's actually, you can't even do this. You can't even deform through incomplete metrics. So somehow as the dimension goes up, the hyperbolic geometry becomes more and more restrictive. So that's just, families get more spread out as you go, increase the dimension. Okay, so now I kind of want to finish the talk with talking about infinite volume, which when I first started grad school, I didn't know this was like something that you would think about. So here's a manifold that I like a lot. It's basically the manifold we started with. It's just a surface, and we cross it with a real line. Okay. And now this has actually, as a 3 manifold, it has lots of hyperbolic metrics on it, usually. So if the surface has genus 2 or more, then this thing has lots of hyperbolic metrics on it. So one thing you can do is that you can actually take one of these isometrically embedded copies of the hyperbolic plane and hyperbolic space, and you could take the fundamental group of the surface acting on that hyperbolic plane, and you can just let that PSL2R, act on hyperbolic space instead of just the hyperbolic plane. And if you take the quotient of the hyperbolic space by that group action, you'll get a surface cross R. Okay? And it has that. In that case, you actually have this nice geodesic surface sitting in the middle, and then it just kind of flares exponentially as you move away towards infinity. Okay, so in that case, we have like some geodesic surface in the middle, and we have this product, and it's kind of like it looks like the geodesic surface on both sides. But you might ask, so we have all these deformations of that hyperbolic metric that come from just deforming that surface. Okay, and so that's like a very 2-dimensional thing, and like the hyperbolic structures on this product will just sort of come along for the ride. But there's sort of a more 3-dimensional thing you can do called the simultaneous uniformization theorem. And it says that the convex co-compact hyperbolic structures on this, which don't worry so much about what that means. It basically means that all the geodesics are contained in some fixed compact set. So that's what I've drawn in the middle, this angular thing. It's like the core that contains all the interesting topology and all the closed geodesics. And so what the simultaneous uniformization theorem says is that, when I have this Fuchsian thing, it kind of looks like just this Fuchsian thing and then flaring, and you have like this product. Well, what Baer says that, if you look off to infinity in that manifold, kind of sitting at infinity is a copy of your hyperbolic surface conformally. And then looking out the other way, at infinity, there's another copy of that surface. And so you might ask, can I actually deform them independently of one another? And that's what Baer's theorem says. So actually, there's a huge family of hyperbolic metrics on this product, and they're not just parameterized by one type image space, but by the product. Okay, so there's this much larger, it's twice as many degrees of freedom in deforming the hyperbolic metric on this thing. So that's one way to just think about this simply, that like the dimension of the family has doubled. Okay, so that's one kind of thing. And then there's another, it doesn't have to be a surface cross R. If you have interesting boundary, then the same kind of theorem is true. Like you can deform kind of the boundary, and that deforms the hyperbolic metric on the inside. So the way you think about this is a hyperbolic manifold is chewy on the outside and crunchy on the inside. It's like hyperbolic, like a crystal, which we would expect to be rigid, but we can deform this conformal thing with the boundary a lot, and like the hyperbolic structure just comes along for the ride. Okay, and now these are just very special hyperbolic metrics. So you might consider the space of all hyperbolic metrics on this manifold, and you can think of this, space of all metrics as kind of like being a space of representations, and it sits inside of this variety that I mentioned before. And the Bayes density conjecture, which is now a theorem due to Bromberg, Brock-Bromberg, Matsumoto, and Oshika, says that actually every hyperbolic structure is kind of a limit of those. So if you take the closure of those nice representations before, which were just parameterized by the Teichner space, then you get all of them. Okay. So there's no hyperbolic structures on this manifold that are just off alone without a family. Right. Okay. And then, close to my heart is this theorem of Thurston's called the bounded image theorem that says if the manifold doesn't have any cylinders in it, so it's it's kind of the opposite of the surface cross R case, that actually the set of all hyperbolic structures on it is compact. Okay. And so you might think before, when we had surfaces, our deformation space was like Rn, and like that's very non-compact. And so this is very different, So this is a much more restricted kind of space. Okay, and then part of my entire career is like finding bounds on the diameter of this in some sense. So Bromberg, Minsky, and I have theorems in the works on this that are too technical for this. And then so this thing is compact, so it's not like and it's a compact set like sitting inside of a variety, so it's not necessarily a subvariety, and in fact, it's not a manifold usually. It's not a variety. It's not a family in your favorite sense, because it's like the defining property of it is that it's just the set of hyperbolic structures, when you give it some topology from this variety. But it can even fail to be locally connected. Okay, so so Bromberg proved the first version of that like certain deformation spaces of hyperbolic 3 manifolds are sort of really wild. Okay, so they're really exotic kind of families. But that's okay, because families come in all kinds, and some of these weird families are like really useful to proving things like the Dane Filling theorem. And we can use manifolds that are pinch negative curvature instead of actually hyperbolic. Maybe maybe they're almost hyperbolic, or we could use cone manifolds. Hodgson and Kirchhoff proved versions of Thurston's theorem using cone manifolds. So you, instead of using incomplete structures, well, they're in the background, but you use these cone structures instead. Or you can just, use all Riemannian metrics, which is intimidating. Just like expand your idea of family to this huge space, and then you get, like the Ricci flow. And Perelman proves geometrization that way, so enlarging your idea of what you're allowed to work with is often pretty useful. And so you could use approximate hyperbolic metrics, or we could consider families of representations, or and that gives you things like actions on R trees, which is like an R tree is like really far from a manifold, and now we have these more exotic things, and that's you start using things from geometric group theory or cat-zero Coop complexes, which Ian Engel used spectacularly recently, and you use algebraic geometry, and actually think about the algebraic geometry of these curves, and look at curves of characters, and think about the moduli space, and maybe you could start counting and using probability, and doing arithmetic and doing number theory, and thinking about the actual number fields and quaternion algebras and division algebras that you're working with, or and then there's things like super rigidity and profinite groups. Thanks very much.